Hey everyone, today we're going to look at topic 510 and 511, which are basically the same topic. We're going to talk about optimization today. Okay, what is optimization? One of the most common applications of calculus involves the determination of minimum or maximum values, which we've been doing a lot recently anyway. Consider how frequently you hear or read the terms such as greatest profit or least cost, least time, greatest voltage, optimum size, least size, greatest strength, and greatest distance. Before outlining a general problem-solving strategy for such problems, let's take a look at an example, and then we'll come back to this guidelines in a second here. All right, so here's an example of what we might want to do. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions should the box be in order to produce a box with maximum volume? Okay, so manufacturers deal with this on a daily basis here. They want to maximize their volume while minimizing their surface area. Okay, so you can see here, here's 5 different boxes that would fit this mold, and we want to think about, all right, which one's going to be the maximum volume? And maybe it's not even one of these that we see here. Okay. How do we do this? A couple guidelines here on how to do this. Identify all given quantities and quantities to be determined. Making a sketch does help. Write a primary equation that is to be maximized or minimized. So the first thing you want to write down is, what am I trying to optimize? Okay. Sometimes you'll have 3 variables in that equation, and that's not good. You want 2 variables. You want an input and an output. That's it. If you have more than 2, you need to write a secondary equation. That's step 3 there. If you don't have more than 2, so if you only have 2, one input, one output, then you can skip step 3. Step 4, determine a feasible domain for your primary equation. And step 5, determine the desired maximum or minimum value by using the techniques discussed earlier, as in the first derivative test or even the second derivative test as well. All right, back to our problem. So our primary equation here is going to be, what are we trying to optimize? We're trying to optimize the volume. This is just a rectangular prism. So the volume of a rectangular prism is length times width times height, which in this case is x times h, or x squared h. As you can see there, there's 3 variables. Not good. So we need to get rid of one of those variables. So we need a second equation. Look at the problem to see what we know to find the second equation. There's your second equation. The surface area is 108. So 108 equals the surface area of this prism. Let's see what the surface area would be. The top and the bottom would be x squared. Right? But this is an open box, so we're not including the top anyway. So the bottom itself is just x squared. The 4 sides are xh, 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 and xh. So 4 xh. So there's our secondary equation. So now you got to choose, do I want to get rid of x or do I want to get rid of h? I think it's going to be a whole lot easier in this equation to get rid of h. So let's solve this for h by subtracting x squared and dividing by 4x. And now we can take what h is and substitute it back in to our primary equation. And now we need to find the critical numbers of that equation. You can do that right now, but I would highly encourage you to simplify this as much as you can before we take that derivative. All right, so for example, we can get rid of one of these x's here, and then I can distribute the other x in. So now my equation becomes 108 minus x cubed over 4, which I can rewrite as 27 minus x cubed over 4. If I take the derivative of that, oh, I'm sorry, but when I distribute this x in, I forgot to put an x there, so it'd be 27x. So I take the derivative of this, v prime, it would be 27 minus 3x squared over 4. To find the critical numbers of that, we set that equal to 0 or undefined. It will never be undefined, but I'll bet it will be 0. So as we set this equal to 0 and solve, we get 3x squared over 4 equals 27. Multiplying by 4/3 on both sides, we get x squared equals 36. So x equals plus or minus 6. All right, so now we're going to make a number line using a feasible domain for this. Okay? What could x be? Well, it's a side, so it can't be less than 0. Okay? It can't be 0 for that matter. So our number line will start at 0. And the biggest it could possibly be, since there's 4 sides and we have 108 square inches, 108 divided by 4 would be 27. So our domain for this really would be 0 to 27. In other words, we don't consider the -6 a possibility. This side length could not be -6. It can be +6. All right, so we're going to test this in V prime by picking some test points out. Let's say if we put 1 in, it would be 27 minus 3/4, which is positive. So we're increasing. And if we put 10 in, it would be negative, so decreasing. So it looks like 6 is a relative maximum. So therefore, our maximum dimensions will be when x is 6, but now we got to figure out what h is going to be. So h would be 108 minus 6 squared over 4 times 6. So that's 108 minus 36 over 24, which is 3. So to maximize the volume of this box, the dimensions of the box must be 6 inches by 6 inches by 3 inches. Example 2, which point in the graph of y equals 4 minus x squared, or points, are closest to the point 0, 2? All right, let's draw a quick sketch of this. So 0, 2 is right here. 4 minus x squared, it's an upside down parabola. So which point or points on this graph are closest to that point 0, 2? So we're trying to find the distance from a point to another point, which means our primary equation here is going to be the distance formula. Distance equals, now we don't know the point that we're looking for, so we'll call that first point xy. The second point is 0, 2. So square root of x minus x squared plus y minus y squared. And that's my primary equation. Now, unfortunately, again, we have 3 variables here. So we need a second equation. This one is very easy. It's given to us in the problem. Y equals 4 minus x squared. It's already solved for y. So don't make too big of a deal out of this. Take 4 minus x squared and put it in for y. So I get distance equals square root of x squared plus 4 minus x squared minus 2 squared. Or x squared plus 2 minus x squared squared. Okay, and if we keep simplifying that, we get square root of x squared plus 4 minus 4x squared plus x to the 4th. So it'd be x to the 4th minus 3x squared plus 4. And that's what our distance formula equals. All right, so now we can take the derivative of that. So d prime equals 1/2 times x to the 4th minus 3x squared plus 4 to the negative 1/2 times 4x cubed minus 6x. And if we simplify that, we can get 2x cubed minus 3x over root x to the 4th minus 3x squared plus 4. So we want to set that equal to 0 or undefined. That denominator will not ever be able to equal 0. So that's out of the picture. But the numerator will equal 0. Let's see here. So if we take an x out, we were left with 2x squared minus 3. So that's going to be either when x is equal to 0 or x squared equals 3/2. So x equals plus or minus root 3/2. So we get 3 critical numbers here. Are they all part of our domain? Absolutely. There's no x's that this can't be. So we're not going to restrict our domain at all here. So we have a full number line for d prime. It's going to be negative square root 3/2, 0, and positive square root 3/2. Pick some test points out here. So let's start with maybe negative 5. And if you put that into d prime, again, we're not concerned about what exactly that would be. We're concerned about the sign, and that would be negative. So decreasing. And these are going to alternate here because of their multiplicities being odd. All right, what are we trying to do here? Remember, we're trying to minimize the distance between these points. So we want the local minimums, which would happen there. So, writing out our answer, the minimum distances occur at negative square root 3/2, comma something, and square root 3/2, comma something. So let's figure out what those y values are. If you put square root of 3/2 back in for x up here, you get 4 minus 3/2, which is 2.5 or 5/2. And if you put negative in, you get the same answer back. So both are 2.5 or 5/2. Which looks like it would be right about there and there. So those distances are the shortest distance. Number 3, a rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are set to be 1.5 inches. And the margins on the left and right are set to be 1 inch. What dimensions should the page be so that the least amount of paper is used? All right. So this is nice. It's already set up for us here. We're going to call this distance x for the print vertically, this distance y for the print horizontally, and our margins are already set. So we want to see what dimensions we would have so that the least amount of paper will be used. So we're trying to minimize the paper. All right, so we're trying to find the area of this paper. That's what we're trying to minimize. And it's just a rectangle, so it's going to be x plus 3 times y plus 2, which once again, we have 3 variables here, so we need a second equation. That second equation is given to us right here, 24 square inches of print. So 24 equals xy. All right, so you have a choice here. Do you want to solve that for x or y? There's no wrong answer. I'm going to solve it for y, and that would give me 24 over x. So I'm going to put 24 over x in for y. And we could take the derivative as is right now, but again, might as well simplify this if we can. So multiply this out, we get 24 plus 2x plus 72 over x plus 6. which is 2x plus 30 plus 72x to the negative first. So a prime then would be 2 minus 72x to the negative second, which will be undefined at 0, but it also will probably be equal to 0 at some point as well. So let's set this equal to 0. And I get 72 equals 2x squared. So 36 equals x squared. So x equals plus or minus 6 again. But again, we're talking about a piece of paper here. We can't have a negative side length there. So again, we're going to want our number line to start at 0. And again, we can't really have that big of a side here. So let's say 24 would probably be the biggest side we can have because the area is 24 there. So it has to be less than 24. So 6 is the only number that goes in our number line. And we're testing a prime. All right, so if you put maybe 1 into a prime, you're going to get 2 minus 72, which is negative. If you put 10 in, you're going to get positive. So that indeed is a minimum. Okay, but the question asks, what should the dimensions be? So at least my paper is used. Make sure you get y as well. So y would be 24 over 6 or 4. Okay. So quick note here, x and y are the dimensions of the print. Okay. The dimensions of the paper, this is 6 and this is 4, then would be 9 and 6. So the dimensions of the paper should be 9 by 6 inches. Okay, example 4. 2 posts, one 12 feet high and the other 28 feet high, stand 30 feet apart. They are to be steadied by 2 wires attached to a single stake running from ground level to the top of each post. Where should the stake be placed to use the least wire? We can use a calculator to figure this out. So we are looking at here, where should the stake be placed to use the least amount of wire? So we're going to try to minimize what y and z are together. All right, so we can make up a variable. In the picture I did that for us here. We're going to let w equal y plus z. So that's our primary equation. We are trying to minimize what y and z are together. 3 variables there, so that's not good. We don't want that here. But there's a couple different secondary equations we could use. We can use one to eliminate y, or we can use one to eliminate z. It doesn't really matter. The one to eliminate y would probably be a little bit easier because it's just x squared plus 12 squared equals y squared. The other equation we could use would be 30 minus x squared plus 28 squared equals z squared. All right, so to do this, let's solve both of these. Sorry, here it looks like a bad 12. Let's solve both of these so we can get them in terms of y. So, sorry, in terms of x. So the first one, take the square root of both sides. It's easy enough. We get y equals plus or minus root x squared plus 144. The second one, take the square root of both sides. We get z equals plus or minus root of this whole thing. I don't know what 28 squared is off the top of my head, so I'm just going to write 28 squared for now. Okay, now I'm going to replace y and z in my original equation with that. So w equals, and we're going to take the positives of these because obviously y and z have to be positive lengths. They can't be negative lengths. Square root of x squared plus 144 plus square root of 30 minus x squared plus 28 squared. All right, the nice thing about this here is that this is a calculator problem. We really don't want to have to take the derivative of this by hand and find its critical points by hand. So we're going to type that into y1. And we're going to type the derivative into y2. So again, set y1 equal to w. And then in y2, you can do the derivative of w with respect to x. And we're going to see where the derivative changes signs at. See where the derivative is 0. And if you're doing this correctly, if you want to pause this video at this point and do that, you go ahead and do that. But if you're doing this correctly, we should get that the derivative is equal to 0 when x is 9. And you should also see that it's going from a negative to positive, which means that point is a minimum. So the question is asking, where should the stake be placed to use the least wire? Well, x should be 9, right? So we know we want that to be. And then 30 minus x would be 21. So we know we want it 9 feet away from the left pole and then 21 feet away from the right pole. But we can just say 9 feet away from the left pole would be fine. The stake should be placed 9 feet away from the 12-foot pole. All right, there's a picture of what that would look like. So you can see 9 is definitely the minimum on this graph. And if you graph the derivative, it would cross 0 at that point, going from negative to positive. Okay, number 5. Rick wants to make Morty a holiday decoration. Rick has 4 feet of wire that can be used to form a square and or a circle. How much of the wire should Rick use for the square and how much should he use for the circle in order to create ornaments with the maximum total area enclosed? All right, so we have 4 feet of wire, and we're trying to maximize the area. So the area of the square plus the area of the circle. And then the perimeter / circumference would be our secondary equation. So we have 4, and that equals 4x plus 2 pi r. All right, we can solve either of those. Solve that for either equation. Solve that equation for either variable. I'm going to solve it for r. So subtracting 4x, dividing by 2, and then dividing by pi. So I would get 4 over 2 pi, which is 2 over pi, minus 4x over 2 pi, which is 2x over pi, would equal r. Or you can write it as 2 minus 2x over pi. Going back over here, we have area equals x squared plus pi 2 minus 2x over pi squared. All right, simplifying that, we get x squared plus pi times 4 minus 8x plus 4x squared over pi squared. One of those pi's would cancel out. So we're left with x squared plus 4 over pi minus 8x over pi plus 4x squared over pi. Taking the derivative of that, we would get 2x plus 0 minus 8 over pi plus 8x over pi. And if we set that equal to 0, if we combine like terms but take out an x here, so we had x times 2 plus 8 over pi equals 8 over pi. So I did a couple of things there at once. And then if I divide, I get my answer of 8 over pi over 2 plus 8 over pi. All right, I'm not going to get into the details, but simplifying that, we would get down to this, 4 over pi plus 4. Okay? So the best way we can do this, and we can use to make it. All right, we want the volume to hold 22 cubic inches, which is about 12 fluid ounces of Coca-Cola, or whatever your favorite soft drink is. But we want to minimize the aluminum. We don't want to use the least amount of aluminum possible. All right, so we want to minimize the aluminum. That's going to be surface area. The surface area of a cylinder is 2 pi RH plus 2 pi r squared. All right, that's got a lot of variables in it, but we can write another equation using the volume of a cylinder, which is pi r squared h. Let's get rid of h by solving for it. So I get area equals 2 pi r times 22 over pi r squared plus 2 pi r squared. And simplifying that, we get 44 over r plus 2 pi r squared. Taking the derivative, we get negative 44 over r squared plus 4 pi r. And if we set that equal to 0, and solve this. Well, first of all, r could be 0. That's a critical number, but that's probably not what we want it to be. We probably don't want the radius of our can to be 0. Solving this, we get 11 over pi equals r cubed. So then r equals the cube root of 11 over pi. Okay, and once again, then what we would do is we would make our number line here. The radius cannot be less than 0, so we don't want that on there. And let's see, the radius probably could not, we don't know exactly what the maximum would be, but it can't be that big. But either way, we're going to put the cube root of 11 over pi on there. Pick some test points. You're going to get negative and positive, which means that would minimize our surface area. All right, so a radius of cube root of 11 over pi inches would minimize the surface area. All right, that is it for optimization. Thanks again for tuning into this video today.